So in this discussion session, we will start looking at the solutions of the Dirac equation which we obtained in the last class, where in search of first order differential structure or first order of derivative operator, we wanted to write a Lorentz invariant kind of differential equation which governs the wave function. We ended up getting the criteria that the equation should look like the first order time derivative should equal to a Hamiltonian which is made up from IH bar del x, which is the momentum operator, multiplied with not some constants alpha 1, alpha 2, alpha 3 and beta, but matrices alpha 1, alpha 2, alpha 3 and beta. These matrices satisfy certain conditions, that alphas have their anti-commutator equal to twice of delta ij, alpha and beta anti-commute perfectly, and the squares of individual matrices of all alpha i's and all the beta square is identity. And then we also realized that this can only be achieved by even dimensional matrices. It can either be 2 cross 2, 4 cross 4, 6 cross 6 or 8 cross 8 or so on. So odd dimensional matrices cannot satisfy these three conditions. So therefore the lowest possibility is 2 cross 2. But in 2 cross 2 dimensions, we found out that there are no 4 linearly independent matrices which we want. We want 3 of alpha 1, alpha 2, alpha 3 and 1 beta. Overall 4 independent matrices. In 2 cross 2 dimensional matrices space, there are only 3 such matrices which satisfy these criteria. So we have to dump 2 cross 2 dimensional space. The next possibility is 4 cross 4. And there indeed we have a case where we do get 4 linearly independent matrices which satisfy that. For example, one possible case of such 4 linearly independent matrices are this, where alpha i's, where the matrices which were 2 cross 2 zero matrix in the diagonal, and sigma I, which are polymatrices, 2 cross 2 dimensional polymatrices in the off diagonal, sigma I, sigma I. When this alpha i's multiply the pi's, they will take all the components multiplied to pi. Zero matrix will remain 0, but the off diagonal block will pick up pi operators. Remember, pi's are minus iota h bar del xi. That's what we are writing pi says. Similarly, the beta part, which is identity in the diagonal and minus identity, and off diagonal elements are 0 cross 0, can be written with multiplication of m naught c square, which is here. Now we also learned that when the operators appearing alphas, betas are 4 cross 4 dimensional matrices, the wave function psi itself is a 4 cross 1 dimensional vector, psi 1, psi 2, psi 3, psi 4. So when we choose to write the whole matrix equation over here in terms of 2 cross 2 blocks, that upper block is made up of 2 cross 2 matrices, one is 0 and one is sigma I, and lower block is also sigma I and 0. Then what we could do, can split the full wave function also into 2 cross 1 and 2 cross 1. So upper block will be called phi and lower block will be called chi. So upper and lower blocks are doublets. Phi is a doublet which is made up of 2 elements like here a, b, and similarly chi is another doublet which is also made up of 2 elements, something like a prime, b prime or cd. So this is the structure which we'll get. I have written one realization of alpha 1, alpha 2, alpha 3, which is off diagonal sigmas, and beta being identity minus identity along the diagonal. You can in general get another combination on some other matrices which also satisfy the same relations in 4 cross 4 dimensional matrix space. But we also know that those matrices which you will generate are just unitary transform version of these matrices. So they are not really different, they are unitarily equivalent. So quantum physics, which is invariant under unitary transformation, should not give rise to new predictions. So in 4 cross 4 dimensional space, this is a choice which is unitarily equivalent to all other choices one can make. Okay, all right. Now with this information, we want to look at what kind of time evolution equation we get it. So suppose this operator hits the first element, the first doublet, then that should be equal to the upper two rows of this equation. That is means this upper two thing multiplying the whole thing over here plus this upper two thing will multiplying the whole column vector here will give rise to IH bar del del t of phi. So therefore IH bar del del t of phi should be equal to C times 0 matrix multiplying phi, which is 0, plus sigma I pi multiplying chi, acting upon chi rather, because pi, remember, is an operator. So sigma I pi acting on chi. On the second term, m naught c square times identity multiplying phi, which is m naught c square times phi, plus 0 matrix multiplying chi, which is nothing. So this is the two terms which you will get. Similarly, for getting the lower doublet chi's differential equation, I should look at this block multiplying the block here and the lower block here multiplying the full column vector here, which will give rise to this differential equation. IH bar del chi upon del t is equal to C times sigma I pi acting on phi this time and minus m naught c square chi. So you see, if I split the 4 cross 1 dimensional column vector psi, it gets differential equation of two coupled doublets. Phi and chi are written in a differential equations which are coupled differential equations. Differential equation of phi is not completely written in terms of phi alone. It depends on chi. Similarly, differential equation of chi does not only depend on chi alone, it also depends on phi. So therefore they are coupled equation. You might have seen equations of coupled harmonic oscillator, for example, where first oscillator's position determines the time evolution of second and vice versa. Similarly here, the first half of the full wave function, psi 1, psi 2, psi 3, psi 4, upper two elements which are phi, their time translation, their time evolution depends on what the values of the lower two elements psi 3, psi 4 are. That means what is chi, and vice versa. Okay, so this is the coupled set of equations we end up with, and we want to look for stationary state solution. That is to say that psi should be coming back to itself after IH bar del del t operation, just like we had discussed in the previous classes as well. For positive energy solutions, stationary solution, this equation should be satisfied. That this operator acting on psi should give me back the psi and the eigenvalue E. That means if I write in terms of phi and chi, this operator acting on this doublet, pair of doublets phi and chi, I should get the E times the doublet phi and doublet chi back. So upper row equation will give me this and lower row equation will give me this. So we are looking for a stationary state solution, that's eigenstate of IH bar del del t operator acting on psi should get me psi back with E. That is equivalent to saying that even phi and chi will do the same thing. And you know the solution of these kind of differential equations are exponential times a constant. So therefore phi will be written as an exponential minus iota et upon h bar up to a constant of time. So this is a differential equation in time, partial differential equation in time. So therefore the constant you will get will be constant of time, but it may depend on other positions. It can be a function of position but constant of time. And similarly for chi also has the similar kind of equation structure. So therefore even the chi would have e to the power minus iet upon h bar times a constant of time, but that can be a function of space. Okay, so overall, therefore, if I want to write down the overall equation for psi, the wave function psi would be just phi of x and chi of x times e to the power minus et upon h bar. All right, and remember these derivative operators are appearing in the left side of the equation set E. The equation set E here has the temporal derivative of doublet phi and temporal derivative of doublet chi in the left hand side. So therefore, if we are looking for a stationary state solution, the left hand sides of this equation will be replaced by E phi and E chi respectively, and right hand side remains the same as it was. Okay. Now further, if we want to look for not only the stationary states of temporal derivative but the stationary states of spatial derivatives as well, that means eigenstates of the momentum operator as well. We all know that the eigenstates of momentum operators are e to the power I p dot x upon h bar. So this operator acting on this function e to the power I p dot x upon h bar throws up the eigenvalue p which appears over here with the wave function back. So therefore, if I want to have not only stationary state in time but eigenstate of momentum operator as well with eigenvalue p, then I can write down the phi of x as some constant now of constant of space as well, so some full constant thing, and then e to the power I p dot x upon h bar. And similarly, chi of x will be a constant chi naught and I of p dot x upon h bar. So therefore, this phi x and chi x appearing over here can be written in terms of this function, and therefore psi will become a constant doublet phi naught and a constant doublet chi naught. This cannot depend on time as well as space, so this is a full constant of a space time. And then e to the power minus I e t upon h bar was already there, and plus I p dot x upon h bar will come, where p is the eigen values of momentum operator. Its component p is a vector here. It is ordinary vector, not operator anymore. It is eigenvalues. Its components are eigenvalues of different p operators. So p1 operator will give p1 eigenvalue back, p2 operator will get p2 eigenvalue back, and p3 operator will get p3 eigenvalue back. And these eigenvalue p1, p2, p3, which are real numbers because they are eigenvalues of a Hermitian operator, will generate this p vector. Okay, so the overall I will have a constant doublet phi naught chi naught, and I would have a constant doublet phi naught chi naught, and this plane wave e to the power minus I e t plus I p dot x, everything divided by h bar. This plane wave multiplies the pair of doublets. So this is still 4 cross 1 dimensional matrix, doublet here, but they are constant doublets, and a plane wave which multiplies. These are the solutions of the Dirac equation which we are looking for. So we have solution of Dirac equation where we have a constant 4 cross 1 times the plane wave. Now this is a very interesting structure that emerges out, and we will now realize the plane wave part we understand. But what is this 4 cross 1 dimensional part which has come about, that we will need to see in more detail. Okay, so let us try to solve these equations together to realize first, is there any relation between the E eigenvalues of the temporal derivatives and P's the eigenvalues of the spatial derivatives. So in Klein-Gordon equation, we knew that E square was equal to P square C square plus M naught square C4. Let us see what do we get at this end. So if I write down at all the derivative operator, del del t will give me E here and E here. This pi operators will give me pi here because of the first equation here, and this pi on chi will give rise to p numbers, real number pi times chi because of this equation here. And similarly, the second equation, the first term on the right hand side, will also become pi times small phi due to this decomposition, this equation over here, which is the eigenstate of the momentum operator. So therefore, the equation will get converted into real numbers times phi and chi. All the operators have acted upon, and we have real numbers E, Pi's, and so on. So the equation which we got down, remember, there was m naught c square appearing in both sides. M naught c square with phi was here, and m naught c square with chi was here. So what we can do, we can take the m naught c square here, and m naught c square from here to the left hand side. So what we will get is this E minus m naught c square times phi naught would be equal to the C times sigma I eigenvalue pi this time times chi naught. Remember, psi had become constant phi naught, constant chi naught times plane wave e to the power minus I e t plus p dot x upon h bar, everything upon h bar. So therefore, this phi naught and chi naught are constant things. We want to know what are these constants, but anyway, first we will write down the structure. So I will get phi naught times in principle e to the power minus I e t plus all this exponential term, and similarly in the second term e to the power minus I e t plus all the exponential term, but these are common to both of them. We can throw it towards the 0. So I will get only equations for phi naught and chi naught which are coming about here. The first equation will become that. The second equation will also develop the similar feature. Only thing we have to care about this, there was a minus sign already present. When I take it onto the left hand side, I get E plus m naught c square acting on chi naught, and the thing which was surviving on the right hand side was the derivative operator acting on phi, which itself has become momentum pi times constant doublet phi naught. So therefore that can also be brought to the left hand side, and I will have a matrix equation which is something times phi naught minus some other things acting times chi naught. It's a doublet equation. This is 2 cross 1 dimensional matrix equation. The lower one is also 2 cross 1 dimensional matrix equation. So these pairs of two doublet equation, this is 2 cross 1, meaning some AB for phi naught and some CD for chi naught should satisfy that. We want to know what is the doublet phi naught and what is the doublet chi naught. So these equations can together be written as E naught m naught c square times identity, 2 cross 2 identity, acting on phi naught chi naught. So this identity 2 cross 2 will hit just this doublet phi naught, and minus c times summation sigma I pi. Sigma is I is again 2 cross 2 dimensional polymetrics. So this block will hit only this doublet chi naught, and I will generate the first equation here. Similarly, the lower equation here can be generated by the lower row of this matrix equation. So you can see it is effectively the whole equation which is obtained after all the derivatives acting is equivalent to some matrix M, 4 cross 4 dimensional matrix M, acting on these phi naught and chi naught. The matrix elements are broken into blocks of 2 cross 2. So this is identity times something here, polymatrices times pi summed over all polymatrices, and similarly here. And the other diagonal thing is identity, but with a different constant multiplied to it. So that matrix acts on phi naught and chi naught and gives me a 0. There are two possibilities. This equation can be trivially satisfied if phi naught chi naught themselves are 0. But if they become 0, this doublet becomes 0, the full wave function becomes 0. That we do not want. We do not want the trivial solution that everything is 0, so all equations are satisfied. That we do not want. Is there a non-trivial solution? Suppose the other possibility is that there is some non-zero possibility, non-zero phi naught and chi naught which do satisfy that. That can be only possible if this matrix M does not have an inverse. Why I am saying so? If suppose a matrix M has an inverse, I can multiply M inverse to the both side. M inverse multiplying 0 will remain 0, and M inverse multiplying M on the left hand side will become identity. So identity acting on phi naught chi naught should be equal to 0. That means phi naught and chi naught should individually be 0. This will happen if M is an invertible matrix. So therefore I do not want M to be invertible. M should be a matrix whose inverse should not exist. And we know from matrix theory, all matrices are not invertible. There are a set of matrices whose inverse does not exist. What are those matrices? The matrices whose determinant is 0. So matrix determinant, if it is 0, we know it does not have an inverse. So therefore, in order to have a non-zero phi naught and chi naught, it is necessary that M's determinant is 0. That means determinant of this M matrix which we have written should be 0. Okay, that means this 2 cross 2 blocks determinant multiplying this and this should be equal to 0. So it is 4 cross 4 dimensional matrix, not 2 cross 2 dimensional matrix. So be slightly careful about it. So there is a 2 cross 2 element here, 2 cross 2 element here, 2 cross 2 element here, and 2 cross 2 element here. So in principle, it is 4 cross 4 dimensional matrix, and this is a good exercise for you to write down what do you get if you write down the determinant of such 4 cross 4 dimensional matrix. If you just multiply this diagonal to diagonal, you will be left with a 2 cross 2 dimensional matrix because it is not a number here, it is matrices here. So you have to do it slightly carefully. So it's an easy exercise actually you should do, and you should realize once you do that, the determinant equal to 0 is exactly the same equation which we obtained for the Klein-Gordon case. That E square is P square C square plus M naught square C4. So therefore, the solutions of determinant M is equal to 0 is the same solution which we got for Klein-Gordon equation. That E, which was the eigenvalue of temporal derivatives, that was the energy, comes up with two signs, positive and negative. So despite we started with the first order derivative structure, we hoped that we will get a single signature E, but the fact that Lorentz symmetry demanded that the wave function should be 4 cross 1 dimensional thing, not a 1 cross 1 dimensional thing, then it could be broken into two doublets phi and chi, and their equations were coupled differential equations. So two coupled differential equations of two different fields together is equivalent to a single equation, a double derivative equation of a single variable in some sense. So therefore we know that the Dirac equation manifestly satisfies Klein-Gordon equation as well, because double derivative level, only that is a possibility. So therefore, when we wrote down the two single ordered differential equation, so the differential equation are all single order, so that we were hoping that due to its single order structure we will get a unique E, but the fact that it is not for one variable alone, it is a two variables coupled, which is equivalent to double order differential equation of a single variable. So this is what you might have seen in Lagrangian approach as well. Lagrangian equation of motion is a double derivative equation of motion. So if you remember Lagrangian scheme of things, del L upon del Q dot and d upon dt was equal to del L upon del Q. So ultimately, if you do this, you will get an equation like Q double dot is equal to V primed of Q. However, if you go to phase space, the same equation is written in terms of Hamilton-Jacobi equation, where Q dot is del H upon del Q and P dot is my del H upon, so Q dot is del H upon del P and P dot is del H upon del Q. This was plus and this is minus. So a double order differential equation is equivalent to two single order differential equations, which is what we are getting here as well, that we ended up on the two coupled differential equations of single order, which is together equivalent to one double order differential equation of a single variable. And that is what it is reflected over here, that it is not much different from Klein-Gordon equation. Our structure that it has to satisfy Klein-Gordon has manifestly put the same content in terms of energy. So we are not getting rid of negative energy solution despite looking for a first order equation. Okay. Now, if this is true, once we have known what is E is plus minus of the same previous quantity, then it is easy to prove from here that from first equation, I know how chi naught is related to phi naught. They should be equal to, this quantity on the left should be equal to this quantity on the right, which you can use the identity which we have just derived over here and write it like this, that chi naught and phi naught are related like this. This is actually coming from the second equation, that you can divide the whole thing by E plus M naught C square, such that chi naught will become this quantity divided by E plus m naught c square. So this was the exercise I was trying to propose, but now you see what it is. Now we knew that ultimately we have this structure at hand. The full wave function can come up with two energies, positive energies or negative energy. So I'm going to write a psi plus for positive energy and psi minus for negative energy. And it is made up of two doublets, phi and chi. Again, I'm going to call it phi plus for positive energy and phi minus for negative energy, and similarly for chi. Chi plus for positive energy, chi minus for negative energy. And ultimately, I know that even those phi plus phi minus can be written in terms of plane waves of positive energy and plane waves of negative energy, plus IET in the exponential or minus IET in the exponential. The minus sign wala thing will be called, the thing with the minus sign in the exponential is positive energy. So the minus sign here will come with a plus, and it should be minus plus here, and plus sign will be declared as a minus. E minus means negative energy solution. So this is how the structure is, both positive energy and negative energy. And since we have demanded them to be a solution, we want it to of the Dirac equation and the eigenstates of momentum as well as temporal derivatives. After all, eigenstate of a Dirac Hamiltonian which was appearing on the right hand side, which was made up of momentum operator, and we demanded for eigenstate of momentum operator. That makes it eigenstate of Dirac Hamiltonian as well. So they should be orthonormal eigenstate. So therefore positive energy eigenstates should be orthogonal to each other, and negative energy states should be orthonormal to each other, and positive and negative energy should not talk to each other, they should be also orthonormal. So there should be full set of orthonormality. Different eigenvalues as well as different energies, the signs are different. Remember, E is completely fixed by P. Its sign is not fixed, but its magnitude is completely fixed. So independently, if I fix only P, if the magnitude of P is fixed, P and P prime are the same, then E and E prime's magnitude will be the same, only sign can differ. And that sign difference is captured by this delta function. The total orthonormality therefore is equivalent to orthonormality in the eigenvalues P1, P2, P3, collectively written as a vector P. They should be the same. Energy should be the same, that means their magnitude as well as the sign should be the same. The magnitude sameness is guaranteed by this Dirac delta of momentum. The sign should be the same, is maintained by this Kronecker delta, that they should be the same sign objects. Otherwise, they will not be normalized to 1. So that is, for normalized orthonormal set of solution, this should happen. Okay, and as we again signify, E plus E minus are positive and negative energy solutions of the Dirac equation. Okay, apart from having positive energy and negative energy, which was already there in the Klein-Gordon equation, what have we earned more in this? So we can see that apart from having a plane wave part, which is this, and positive energy solution and negative energy solution, which was already there in the Klein-Gordon. This part was common. In the Klein-Gordon equation also this exponential came about. The new thing is this pair, phi naught chi naught doublets, which is the 4 cross 1 dimensional vector written in terms of two cross 1 dimensional vectors. What are these? So now we will focus attention to what are these. So first, we define something called a helicity operator. What is helicity operator? It is an operator depicted by lambda. That operator is just projection of momentum, that is the normal vector of the momentum, unit normal along the momentum direction. Like operator divided the momentum vector divided by the magnitude of the momentum, and dot product with S. S is some matrix valued vector. That means its X component is some matrix, its Y component is some matrix, and its Z component is also some matrix. And the matrices which are going to be put in the X component, Y component, Z component are H bar by 2, sigma X in the diagonal, and everything else is off diagonal. H bar by 2 here, sigma Y, and off diagonals are 0, and H bar by 2, sigma Z, and off diagonals are 0. So the components of this S vector are two copies in the diagonal of the polywave matrices. So this is therefore is a spin operator. Remember, sigma polymatrices for 2 cross 1 dimensional case, spin up, spin down, spin down, spin up kind of thing. Sigmas used to measure the spin for 2 cross 1 column vectors. So therefore, individual sigma matrices can measure the spins of either phi naught or chi naught. So these are like some spin object. It looks like it has some spin and this has some spin, because polymatrices can act on this and polymatrices can act on that. But this new S operator, which is a 4 cross 1 dimensional vector, which is a 2 cross 2 block in upper diagonal and 2 cross 2 in the lower diagonal, is a spin operator for the 4 cross 1 dimensional vector, psi 1, psi 2, psi 3, psi 4. This can act on a 4 cross 1 dimensional vector. So therefore, this is the spin operator for the full wave function. So what we are doing, the helicity which we are defining a new operator as, is just the projection of the spin operator along the momentum along which the plane wave is moving. Plane wave has some momentum p, eigenstate of momentum operator. That means it has some direction along which it is moving. And it is moving with certain spin. Spin is also a vector quantity, as we wrote down. Polymatrices, some operator times I, some operator times j, some operator times k. So therefore it is matrix valued vector. So this is spin operator has, spin matrices have some direction I, j, k. So I take the dot product and I get a matrix which is an operator, but along the direction of the momentum. That thing is called helicity. Helicity is the projection of a spin operator along the momentum with which particle is moving. Okay. So now this new operator helicity, first we should verify that it commutes with the full Dirac Hamiltonian. The Dirac Hamiltonian, remember, was this. The Dirac Hamiltonian which we had written over here was this here, the first line. And in this, alphas were also made up from polymatrices in the off diagonal, remember. And this time the spin operator which we are trying to make helicity operator have spin operator sigmas, polymatrices in the diagonal dotted with the p. Previously it was multiplying in the off diagonal. Now this is a useful exercise actually, that this lambda commutes with the previous Hamiltonian, Dirac Hamiltonian. That you should prove. This is a homework exercise, 2 lines exercise one should do, and you will be able to prove that this operator, which is made from sigma dot p here and sigma dot p here, commutes with the Dirac Hamiltonian, which was written as the first line. Just convert the momentum operator to their eigenvalues and you can verify that sigma dot p, in that case previously it was appearing as sigma dot p in the off diagonal, and they commute. Okay. So if two operators commute, that means they can have simultaneous eigenvectors. So that means the solutions of Dirac equation can have eigenstate of helicity operator as well. So not only the full solution of the Dirac equation, which was plane wave times a 4 cross 1 dimensional vector, now we know it is a doublet of spins, and that thing would be an eigenstate of the full Dirac Hamiltonian as well. So the full solution of the Dirac equation is identified by actually 4 quantities, the 3 momentum P1, P2, P3, that will fix the total energy's magnitude, then a sign, whether it is positive energy or negative energy, and then there is a helicity element which is also there, so call it small h. So ultimately the full solution of the Dirac equation, which we just wrote down here, apart from having the plane wave part and the 3 momentum which is completely fixing the magnitude of energy, would have a sign of energy which is free that you have to choose, and the helicity of this, which is also an eigenstate possible, so it has some helicity. What are the possible values helicity can take? So let us do an example. Suppose the particle is traveling along the z direction. That means momentum has only one component along the z direction, xy components are 0. In that case, if it is having only one momentum direction, the projection of a spin along p, s dot p divided by magnitude of p, will just be sz, because magnitude of full vector p divided by its magnitude will just give me unit vector along z direction. S dot unit vector along z direction will just give me sz, and sz for 4 class 1 dimensional space is just h bar by 2 sigma z in the diagonals. That means h bar by 2, 1 minus 1, and then 1 minus 1. You see, this is the helicity operator for a particle which is moving along the z direction, or the plane wave which is moving along the z direction. This matrix is simple enough. You can see that it has 4 eigenstates, 2 distinct eigenvalues. You can solve this eigenvalue equation. You will find out equation like this: lambda plus 1 squared times lambda minus 1 squared should be 0. That means it has 2 eigenvalues plus 1 and 2 eigenvalues minus 1. Therefore, there are 2 eigenstates with energy plus h bar by 2 and 2 eigenstates with energy minus h bar by 2. You can clearly verify, you can check that this state 1, 0, 0, 0 is an eigenstate of this operator with eigenvalue h bar by 2. Similarly, eigenstate 0, 0, 1, 0, the third element being 1 and all other elements being 0, is also an eigenstate of the same operator with eigenvalue h bar by 2. While if I put 1 in the second place, 0, 1, 0, 0, then it is an eigenstate of the operator sz, or helicity operator, with minus h bar by 2. And similarly, 0, 0, 0, 1 is also an eigenstate of the helicity operator or sz operator with eigenvalue minus h bar by 2. So this, you see, if particle moves in the z direction, then there are 2 possible choices of helicity: plus h bar by 2 and minus h bar by 2. They are degenerate states. That means there are 2 eigenstates which share the eigenvalue h bar by 2 and 2 eigenstates which share the eigenvalue minus h bar by 2. Actually, if you can work out, you can prove that even if particle were moving along the y direction, then the helicity operator will become sy, and it will be sigma y, which will be off diagonal matrix in the diagonal. So this 2 cross 2 would not be 1 minus 1, it would be off diagonal. But still, you can prove that again. It so happens that despite its off diagonal structure, it has only 2 eigenvalues, which is again plus h bar by 2 and minus h bar by 2. So therefore, we saw in general, you can prove that it can have only 2 eigenvalues in any direction it moves, h bar by 2 or minus h bar by 2. So therefore, the full eigen solution of a Dirac equation has a structure. It is identified by 3 momentum numbers p, signature of the energy lambda, and helicity either plus h bar by 2 or helicity minus h bar by 2. And the full wave function will be, for example, plus h bar by 2 is 1, 0 so 1, 0, 0, 0 can be a case, or 1, 0, 0, 1, 0 can be a case, and their superposition is also an eigenstate with the same eigenvalue. So in general, a phi naught multiplying 1, 0 and chi naught multiplying 0, 0, 1, 0 together should generate for me this. So a phi naught, some constant, let us say multiplying 1, 0, 0, 0 and some other constant multiplying 0, 0, 1, 0, they both have the same helicity eigenvalue. So therefore, the combination also has the same helicity h bar by 2. So upper block, if you are going to call phi, so this is phi naught, lower block will be called chi naught, and I know phi naught and chi naught are related as the exercise we just performed, that the phi naught and chi naught are related by that, because this is the lower block of the Dirac equation. So overall, the full solution therefore becomes 1, 0, this is phi naught, let us say, then this is chi naught, The superposition of this has become chi naught, and they should be related like that. Phi naught and chi naught should be this. And the plane wave with positive energy. Similarly, or positive or negative energy depending upon E lambda. E lambda is positive, E lambda is positive. If lambda is negative, E lambda is negative. Similarly, for negative energy eigenstate, I can either have a 0, 1, 0, 0 or a 0, 0, 0, 1 or a superposition C primed plus D primed. Again, when I combine these two, upper block will become something phi naught and lower wall block will become something other chi naught, and they should be related like that. So upper block is phi naught and lower block should be this factor times phi naught. So you see the helicity with negative helicity eigenstate is something like this. Positive helicity will be 1 here and 1 here, first and third element. Negative helicity will be second and the fourth element, non-zero, and they are related by this thing because they have to satisfy the Dirac equation. So these are the eigenstates of Dirac equation. They have come up with what? Momentum, which was already there, and sign. This much was there for Klein-Gordon equation as well. Momentum, which will determine the total magnitude, and the sign of energy. The new piece is spin or a helicity structure. It comes with a new helicity term, helicity property. Spin along momentum direction. Previously, it has a 1 cross 1 dimensional vector for Klein-Gordon, so there was a no spinor part. Now this has a spin structure. Therefore, this wave function is called a spinor. All right. So this is fine. This is a new theory, Dirac equation, which gives rise to spinor part and new properties. But still, we do not have a solution to negative energy solutions. Again, our hope was if I write first order differential equation, I will get a single signature energy, which has not realized. We have a very double signature kind of energy which was already there. Okay, so therefore we could not get rid of this problem even with the first order differential equation structure, because we could not get first order decoupled equations. We have coupled equations which ultimately becomes equal to a second order differential equation. So it looks like if I demand special relativity compatibility, I would invariably lead to a negative energy solutions as well, which are problematic because probability density cannot be defined. So there were many attempts of understanding if special relativity has to be respected. Second order differential equation doesn't work. First order differential equation also seems does not working because it predicts negative energy states. And if particles can have negative energy, their probability density will come into question. How do I interpret quantum mechanics then? So there were various proposals. One proposal was the negative energy C by Dirac, where he argued somehow nature works in a way that all the negative energy states which are allowed are already full. They are fully occupied. Remember, in the structure, each state for a spinor can be accommodated with either plus or negative sign, spin, helicity h bar by 2 or minus h bar by 2. If all of them are occupied, being fermion, which we will see more detail in quantum field theory, cannot accommodate more. So Dirac's proposal for this Dirac equation was that negative energy states are completely occupied. So therefore, there cannot be any new particle with negative energy. Only thing which we can have is a positive energy. This is a working ad hoc solution being proposed. Or one has to give up the notion of probability density which was predicted by the continuity equation. So therefore, we have to interpret that whatever is coming is not probability density. Probability is only charge density. Charge density can be positive or negative depending upon charge. Okay, so then probably we are talking about fields which we are talking about wave functions which have some charge, and if they have some charge, they will talk to electromagnetic field outside. So we should write down a special relativity compatible Hamiltonian of a charged particle. Right now we have written for a free particle. We should write down for charged particle talking to electric field. That attempt we should do. Or the other only possibility which we are left with, just like when we were doing Klein-Gordon equation, we were left with that the size appearing over here cannot be taken as a numbers, meaning that they have to become operators, so that the density operator, the density probability density which we were interpreting, they should all become operators, and then they should act on some certain things to get rise to numbers. All this indicates that we are talking about a theory of multi-particles. It is not a theory of a single particle. And there is problem if I try to enforce a single particle interpretation, we are led to either multi-particle description or wave function themselves becoming operators. All of them is hinting towards one possibility, which is that we have to let go of the quantum mechanical structure at special relativity if we want to be truthful to relativity, and therefore make these psi's into operators themselves. Operators dependent on position and time. Remember, the wave functions were x and t. When we make them operator, they will no longer be 4 cross 1 dimensional things as we have discussed, because we were looking for a solution of operator previously. Now we will give up that notion that they are themselves vectors. They will become operators themselves. In what dimension and what matrix, that will all be known when we try to convert them into operators, and that is the domain of quantum field theory. So we see that both attempts of first order and second order invariably leads us to the structure hinting towards a quantum field theory. And now it looks like there is no escape but to deal with quantum field theory, develop a theory which talks about fields and not about wave functions. And that is what we will try to do in the next class onwards. Okay, so I stop here.